Yeah, hello, welcome everybody to our seasonal school on network federated learning. We continue today with a high caliber lecturer. We have the great pleasure to have Professor Simo Särkkä telling us about parallel and distributed methods for state space models. So Simo is an associate professor with Aalto University and an adjunct professor with Tampere University and Lappeenranta University. He's also a fellow of the European Laboratory for Learning and Intelligent Systems, or ELIS, and the leader of AI Across Fields program within the Finnish Center for Artificial Intelligence. His current research interests, or his long-term research interests, are in multi-sensor data processing with applications in location sensing, health, and medical technology. He has authored or co-authored around 150 peer-reviewed scientific articles and 3 books. So we are really happy to have Simo now giving this lecture. Thanks a lot and take it away.
So thank you, Alex, for the introduction. And indeed, I'm happy to give the lecture. So this is related to federated learning, but it's also, well, it's on the side of federated learning in the sense that I'm going to talk about more generic parallel and distributed methods for state-space models, but actually they are very useful also in implementing federated learning methods. And my lecture is from like classical point of view. So the connections to federated learning is, well, I would say a bit beyond my lecture, but I'm going to describe the methods and you can continue from that. So it's also an active research topic. So that's why I don't even know all the connections yet. But anyway, so the topic is about well, parallel and distributed methods for state-space models. Well, we will start by, well, defining the goal of the methodology, basically, which is also goal. Well, our goal is to understand the methodology. And then, well, we will take a look at those actual algorithms. Then something about implementations, and then examples of results. And then we will conclude this theoretical part. But then I will also show some examples in Colab, so how you can actually implement them. And we actually have open source implementations available, so you can actually run them yourself as well. So let's then start by the goal. So what is the problem that the methodology, in a sense, is trying to, well, solve? So these probabilistic state space models, they classically are related to modeling of dynamic systems. So, for example, in target tracking, so over here we have of course, toy example, but it's actually quite realistic in the sense that we have 2 cars which are moving here, and then we have multiple radars which measure, for example, the distance or direction or both. And then the movements of the cars can be modeled by using dynamic model of the state space model, and then these radar measurements can be modeled with the measurement model, which is also part of that. And in an abstract sense, well, state space model is also called hidden Markov model. So on the top right, we can see that we can think state space model as a sequence of states which move to the right, which is the direction of forward in time. So that X is hidden. So it would be, for example, the unknown position of the car or position and velocity of the car, the vector of them. And then we get some kind of observations Y, which are somehow related to X. So both X and Y are vectors, but we don't know X, but we only get to see Y. So these Ys would be like maybe stacked radar readings from each of these sensors. But anyway, so in target tracking, that would be the problem that estimates the position trajectory of a car or an airplane from some kind of sensor measurements. And then in spacecraft guidance, well, it would be the sensors, again, they might be, for example, gyroscopes and actually radars. For example, like in moon landing, they used a ground radar to track the height. And then you have multiple different sensors. And then you can also model the dynamics. So this X has dynamics, for example, by the gravitation law, or the Newton's laws, or even Einstein's general relativity based models, which are still stochastic models, so it's actually a Markovian model. And in machine learning, okay, so in this context, well you can also see target tracking problems as applications of machine learning, in the sense that you're trying to learn what is the trajectory given the observations. And that also extends to more generic time series models. So in many cases, time series can be modeled as some kind of finite order Markovian model, where we get some kind of observations. So there are a lot of applications in machine learning literature on the use of state space models for that purpose. And well, there are continuous state space models. So the state might be the position, for example, it's taking values in some vector space. But then there are also speech processing applications where the states might be the syllables, for example, or letters or something similar. And then when you want the problem of understanding speech, for example, corresponds to like a determining the unknown, like a words based on the sounds that we observe. So that is one application. And that links to audio signal processing. So more generally, we could have some kind of music snippet, and then we observe some noisy version from it. So that's also an application of state space models. And biomedicine, there are a lot of applications. But anyway, so mathematically what we have is that we have a Markovian dynamic model. So this X is a vector, and then Y is a vector of measurements. So we model the dynamics by saying that what's the probability of xk given xk minus 1, and then measurements by what's the probability density or distribution of yk given xk. And this k is now the time index. So this is where we want to do inference. And there already is a big theory of how to do inference in this kind of models. So it's a Bayesian model. So in principle, you can kind of just form the joint model and then use some computational, like MCMC method or gradient descent or something like that. But then there are more efficient algorithms designed for these kinds of models. And they are historically called Bayesian filters and smoothers, especially Kalman filters and smoothers, and their nonlinear versions are very much used in many fields of machine learning as well. And in the case of speech processing, for example, SSMs, there's something called forward-backward algorithms, which are actually filters and smoothers as well. And then there's a classic Viterbi algorithm, which is especially used in communications, telecommunications, in decoders, and also it's also commonly used in machine learning applications. And so the filters and smoothers can be seen as the sequences, so that there's a forward pass with the filter, and then backward pass with the smoother. And also in Viterbi algorithm, there's a forward pass, which is not a filter, but does a similar thing, and then backward pass, which then kind of propagates information backward as well. But there's one thing is that because there's a clear forward pass and backward pass, so if we have a, say, federated case or more generic distributed case, we want to do things in parallel, actually. So we want to have some kind of method where, like, the previous or the current result doesn't depend on the previous one in a sequential manner, because if you have a purely sequential process, there is no way to parallelize. We need to do it in a certain order. And in this classic formulation of filters and smoothers, we have that problem. that it is sequential and we cannot cut it, and we cannot like split this into multiple servers or cloud nodes or processors without breaking the method. So one way to say that is that, okay, so even though these efficient algorithms have been designed specifically for these kind of models, and they are classically even optimal in the sense that they only need a linear number of operations with respect to number of data points, they are not optimal in the sense that we can do better with parallel computing. But it also turns out that we cannot just put the filter in a parallel computer and expect better results because it's inherently sequential. So that's why we need to do something else. And so the context that actually that I'm going to discuss is in parallel processing units, so GPUs, which are not distributed as such, but actually in the sense of developing the algorithms, we can think them as distributed systems in the same sense that you have seen for the federated learning, because they contain a huge number of cores inside where we want to do computations like in parallel. There's a question, isn't Kalman filter a specific case of Bayesian filter? Yes, exactly. That's what I was trying to say, is that Kalman filter is one of the special cases. And then, well, yes, so the easy thing in GPUs is that they are shared memory devices, so that you don't actually have the communication constraints between the nodes. So it's slightly easier than a generic distributed system. But anyway, so all the principles which I'm discussing here also apply to distributed systems, but then you need to also take into account the communications. But anyway, GPUs, they're devices with huge numbers of cores, and they are actually available in many, at least gaming computers and also in desktop computers nowadays. And they can run millions of, well, okay, so maybe not millions, but at least thousands of execution threads simultaneously. And they are very, very suited for parallel computing, and that's why they are, well, used in machine learning and not a lot nowadays. So for example, TensorFlow and PyTorch are libraries which the main aim is to support GPU computing. Indeed, TensorFlow and PyTorch. But the programming model is a bit different than normal GPUs, because, well, you don't have just purely sequential operations, but you need to take that parallelization into account. So you need to somehow explicitly put or design the algorithms so that they can be parallelized. Yes, so parallelization means is that we have multiple tasks, and then we want to do something independently and then combine the results. So these tasks, so we don't need to wait task 1 to finish before we do task 2. So, but we cannot do that with any algorithm. For example, filter as such doesn't work because we need to have the results from the previous step to get the results for the next step. So Alex commented, tasks could be completing partial sums. Yes, so in some cases, actually, in the case of like if you have independent summation, like a batches, so that is actually easy to parallelize. So in that case, it happens that you can actually do it. But in the case of filter, those sums are not independent because the result explicitly depends. So it's a recursion. So in some cases, actually in this case, we get more trouble. Indeed, just like a pure independent summation is something called embarrassingly parallel problem. So they actually arise when you compute, well, the gradient for a training set. So that's why they are so popular in deep learning. I mean, the GPUs, because they contain these trivially or embarrassingly parallel problems. But it turns out that people have been thinking about parallelization of sequential problems before. So there's something called a classical all prefix sum computation problem, which is just like a computing of it's basically cumulative sum. And the problem is that if you think how to parallelize computation of cumulative sum, it's not really trivial because you need to kind of add things to the previous. But there is a set of algorithms that can actually do that. You need to build a tree. We will see that in a moment. But it turns out that this same idea can be extended from computing of summations. So summation is something called associative operator, and that associativeness is actually the only thing that we need for to do kind of a divide and conquer type of methods in parallel, and also in distributed manner. But the question is that how can we do this for state space inference, and especially for Bayesian filters, Kalman filters, Viterbi algorithms, and so on. Yes, and the method that we have is, which is the classic prefix sum computation method, is something called scan algorithm. Another name is that the all prefix sums algorithm or associative scan. I will explain. So this question: where can I find more details on this reduction of sequential algorithms to all prefix sum? I have all the citations in these slides. So just stay tuned. And so it needs the associative operator reformulation of filtering, smoothing, and Viterbi. So we need to reformulate those, and then it will be suitable for GPUs and for parallel clusters. And it turns out that actually TensorFlow already supports that kind of thing. And so we will see examples unless we run out of time during this hour. But anyways, so instead of doing sequential computations, so it does a pass, like up pass like this, where each of these levels can be computed in parallel, and then a down pass. And then it like semi-magically manages to still recover the same result. So how do you actually do it? So we can first take a look at that all prefix sum problem, which is the classic one which was solved first. So what it means, it could be called the cumulative sum problem as well, if it clarifies. So that we have a sequence of numbers from A1 to AN or some other objects, and we wish to compute this kind of all prefix sums. So first element is A1, then we have A1 plus A2, then A1, A2, A3, and so on until A1, all the terms summed. And now the key thing is that, well, there is an algorithm which can compute this in parallel, which we will see in a moment. And it turns out that we can also define all prefix sums for any associative operator. Okay, it's just like, let's call it this diamond. So it would be A1 diamond A2, or A1 operator A2, A1 operator A2, operator A3. So for example, matrix multiplication would do, matrix summation would do, and many other associative operators. So associativeness means that when we have a A1 operator B, so we can either do this operation first and then apply C, or do A first and then apply it to B operator C. And then we need to have some kind of neutral element. In the case of summation, this neutral element is often denoted by 0. In the case of multiplication, it's also often denoted by 1. And in the case of matrix multiplication, it would be the identity matrix and so on. But the thing is that if we did this in a trivial manner, or not, well, at least in a sequential computer, so the operation to compute the prefix sum would be something like we start from S0 is 0, and then we loop from 1 to n, and then always compute the next one as using the previous one and then the current element. But the problem is that this is an ON algorithm. And because in this loop, this SI depends on SI minus 1, there is no like a trivial way to parallelize this. So we cannot just do parallel 4 here. But it can be done. So the basic idea is here. So for example, consider this prefix sum. So we want to compute all prefix sums 1, 2, 3, 4, 5 until 8. So what we can do is that we first put them down here. Then we compute this kind of, we combine the elements like 1, 2, and 3, 4, 3, 4, and 7. And so we compute all of these. So for example, from here we get 7 and then 10 and then 36. But we are not done yet. So, well, we have some of the results already. So this is the prefix sum at element 2. This is at 3. So we basically have every second. No, but anyway, well, we have some partial results of the prefix sums, I would say. But but the key thing is that at least this operation can be done in all log n steps. Just a moment. I was misguiding you a bit. So we only have these only have one element actually yet, because only this one is actually the final prefix from the last element. So we need to do something else. But anyway, this can be computed in parallel because each of the levels can be computed in parallel. And because this is the full binary tree, we have a log n levels. So we only need to do like a log n time steps. So in a parallel computing terminology, the span complexity is log n, or the work complexity, not just a moment, span complexity indeed. And the same idea can be also done for any general associative operator. So we can also do matrix multiplication version of this, but we are not done yet. So this is the upsweep, and the magic happens actually in the downsweep that we do. So we can then do a downsweep by, so we assign left value to each node. So the root has L is 0 or the neutral element, then every left child inherits the present value L. So for every left child, we get L, and then depending on where we are, we copy it to the left. So for example, from here, we get the left child's these tens. And then every right child gets the left child sum plus the current L. Right child gets the left child sum plus current L. So this 3 plus 0 gets 3, and so on. And so if you look at this operation, so this also can be done by starting from upperst level. Then we can do these levels in parallel, which also has a log n, log n number of time steps needed. And then it turns out that actually this result will be, so we need to still add these original elements to these results. But anyway, by using these log n steps, we can actually compute the full prefix sum in log n parallel steps. And this is indeed the all prefix sums algorithm. And the nice thing is that, as I mentioned, so this works for any associative operator. We don't need to have a summation. We can have a matrix multiplication. We can have anything. And it turns out that we can also reformulate filters and smoothers so that it becomes associative operator. So this is just a demonstration with concatenation, what actually happens. Maybe we can skip this because this is demonstrating the same thing. But then there is a in-place algorithm also applied by Plelocht 1990, which computes the whole prefix sum upsweep and downsweep in using ON storage. So you don't actually need to do the tree at all, but you just have a upsweep. So there's a parallel loop over here. Sorry, this is MATLAB, but and then downsweep. So there's also a parallel loop. I also have a Python version of this, actually, in a moment. But then, so the details are a bit complicated, but as I mentioned, so you can actually reformulate filters and smoothers in this kind of formulation so that they are associative. And without going through the derivation is what happens. So the classical Bayesian filter looks like this. So there's a prediction step and then the update step. And indeed, it's a forward recursion. And then in this reference, in transactional automatic control, we were actually showing how to do that in an associative formulation. So it turns out that these elements need to be densities. So that there is this kind of xk given yk and x's from xk minus 1. So this is the core element or the first component of the core element in our prefix sum. So they are not numbers, but densities. And then we have this G, which is the kind of predictive likelihood of the measurement. And then if we define the element space to be this one, and then we define our associative operator to look like this, where this combination is that we have a fi, gi, fj, gj, and they are combined to this ij versions. And we define operator like this. So it looks a bit like the update, but it's not quite that. And then we have the combination for the G, which looks like this. So it resembles some parts of the computation of this normalization constant, but not quite. Then it turns out that if we actually compute this operation, then we will get the result that contains the filtering result and then the normalization constant. And well, so this is associative. So it turns out that we can actually use these procedures and replace the summation with this operator and parallelize the filter to log n steps. And the derivations are indeed this article. So this is the filter, and then you can also parallelize the smoother in the same way. Actually, I think that I have it there. But anyway, so this is the filter, and then as we discussed in a moment ago, so as a special case, we get something called Kalman filter from this. For concreteness, what these look like is that so the element will contain matrices. So there are 3 matrices and then 2 vectors. So A, B, C, eta, J. And what they actually define is that they parameterize these distributions F and G. So that they are like a linear model for the mean, and then the covariance, and then like information Gaussian density parameter for G. And then each of these elements, also in the prefix sums algorithm or scan algorithm, are represented by these tuples of matrices, and then the combination operator becomes this set of matrix operations. So then if we just plug in like this definition of element and this definition of an operator to our prefix sums methods, we can actually do that Kalman filtering in parallel. And coming back to distributed case, this kind of also works in distributed case except that you need to communicate like these matrices communicate matrices from between the nodes I and j. But that's I'm going to go to that. But anyway, so if you were implementing a federated learning methods for state-space models in a distributed system, you might need to also communicate this to some place. At least if you want to do exact inference instead of approximate. And in the smoothing case, well, the elements will be this kind of block conditional densities. And then the operator is slightly more simple than in the case of filtering. And then it turns out that you can show that this backward version of a prefix sum will be the smoothing distribution. And as Kalman filter is a special case of Bayesian filter, then something called Ralston-Sheeple smoother is a special case of the Bayesian smoother. Then this operator reduces to a set of matrix operations like this. And well, there is some recent work from ours for extensions to nonlinear cases. So we can also extend to extended Kalman filters, which are Taylor series-based filters and motors. And then because, well, you have a slight challenge with the linearization, so you can actually implement only like smoothers, and especially iterated extended Kalman motor can be used. And then also other iterated sigma point methods, like unscented Kalman filter and smoother kind of methods, can also be implemented like this. So there's a ICASP paper on that, which is also in archive. And it also turns out that you can do hidden Markov models. Well, of course, in hidden Markov models, those are forward and backward methods are just Bayesian filters. But then there are also other kinds of methods, something called the max product methods. And one of them is the Viterbi method. But what we have is that so HMM in this terminology is a discrete state space model, which means that this X just takes a finite number of values. They could be, for example, syllable IDs in speech processing. And in classic like Bayesian graphical model formulation, they are formulated in terms of something called potentials. And then the whole inference reduces to computing sum products or max products for this kind of thing here. So you can take a look at this article of ours if you are interested in. And then these parallelization elements are now these potentials. And then there's, for example, in the sum product method case, so the operator, the associative operator will look like this. So it's just a sum product basically of two like potentials, pairwise potentials. And then in the max product case, we can replace this summation with the max. And it's also possible to do Viterbi method. So actually, some of that is in that article, and then not all the details though. Implementations. So if you actually want to use them, so one way to do this is to, well, you can program GPUs with the CUDA framework from NVIDIA, or then OpenCL framework for more generic GPUs. And then especially for NumPy, so NumPy is a Python compiler. So there is also a target so that you can compile the Python code to CUDA code. So on the right, we have examples of that. So there's a CUDA cheat. And this is, for example, implementing the prefix sums using the Prefix methods, which can be compiled into GPU code. And so there's a pre-scan, we initialize that, and then there's the up pass actually here, and then the down pass could be done in a similar way. instead of using this compiler, you could also use plain C or C++ or more like CUDA-C, which is fun to write, yes, but it's more tedious to debug, for example. And okay, so on the right, there's a couple of examples of that. So, okay, some hints how you would implement that in practice. And actually, this code works directly in Colab because it has GPU support. So if you want to try it, well, or try to program, use CUDA in Colab, it's completely possible. And how to implement these filters and smoothers in CUDA. So you could just replace this summation operator, which is appearing here, with that operator that we have, and then these temps actually would be the tuples of the matrices or some other representations of the densities. Okay, but actually, if you try to do that, you will notice that this, for example, the NumPy has limited support for matrix routines in kernels. Then another way, if you want to actually do it, would be to use the C++ CUDA, which supports, for example, the eigenmatrix library. So that makes life easier. Another way would be to use OpenCL, which is more generic programming environment for GPUs. And so it's a bit tedious, but of course it's fun to try that. But there are other options, because it turns out that because this associative scan is actually quite old concept. So it has been used in parallel computing for 30 years at least. So someone has already noticed in TensorFlow, for example, that it's a generic or very useful generic primitive operation. So TensorFlow has the parallel associative scan operation. So which basically implements this kind of method, but much better than I was able to write it. So it already has all the GPU support and so on. So, and it turns out that also JAX has that as well. So that provided that we can write that associative binary operator, then all we need to do is to call this associative scan to actually implement it. And it also turns out that if you look at least it used to be in experimental part of TensorFlow. So there is even an implementation of this, our method. So someone had noticed that. I don't know anymore if it's there, but you can check. And so indeed, we have examples. We can take a look at these examples in a moment, but these are openly available. So there are Colab implementations of this, of the Kalman filters, or specifically, and then of the nonlinear versions as well. Experiments. So what we get if we actually run these in GPU and CPU, or like in multi-core CPU and a GPU. So what happens is that, well, in CPUs, we typically have less than 100 cores, even in high-end server computers. So what happens is that, so we get a certain level of parallelization, but then it kind of diminishes. So we don't have a perfectly logarithmic complexity for the parallel version and the linear for the sequential one, but there's only like a shift. So maybe summary here, it's a bit logarithmic, but you can't really see it. But certainly this parallel version tends to be much faster because it still parallelizes. But in GPUs, we get much better performance because we easily can have tens of thousands of cores, even in GPUs, which we can actually use ourselves. And more you have, the better, because it should be logarithmic in the number of data points. So how the number of cores is related is that, of course, we can parallelize only up to number of cores. So it's not going to be logarithmic perfectly. And okay, so this is for nonlinear systems. but anyway, we should see the same kind of effects here. So this is using the iterated Taylor series based approximate Kalman filters and also the sigma point versions. And then HMMs, well, you get similar effects also over here. Conclusion. So we were discussing that, well, state space inference for starters, and then we went into all prefix sums. So it turns out that something called all prefix sums can be computed in parallel using the scan algorithm, of which one is by Peloch. But there also exist, by the way, distributed scan algorithms and all kinds of fancy scan algorithms. And all we need to do is that we just define our primitives, and then we use those already implemented fancy distributed scan algorithms, which actually support or implement all the communication details as well. So, but the background is that this sum can be an arbitrary associative operation, and well, but this framework is useful especially for parallel computing in GPUs, but also for distributed systems. And it turns out that inference in probabilistic state space models can be reformulated as a sequence of associative operations. And in particular, we get a Kalman filter, Bayesian filter of filters and smoothers and Viterbi kinds of methods from that. And then for the implementation, we could implement everything with CUDA, but luckily TensorFlow and JAX, maybe also PyTorch, I'm not sure, already has these implementations of the scan primitive in them. And so the references are here if you want to take a look. You can also find them on my webpage. So that these are the classic references, generic one, to my book on Bayesian filtering, and then we have this temporal parallelization articles, well, all from last year actually. And feel free to ask questions. In the meanwhile, I can also go to this example. So you can find these examples on my webpage. If you Google for my name, you should be able to find this kind of page. And there's even advertisement of this school. And so somewhere, if you search for temporal, okay, so this is temporal parallelization of control problems if you're interested using the same idea. But then, for example, this one is for the HMM case. And then we have, so this is for the filters and smoothers. And there's that link of code examples. So if you want to find the examples which I'm going to show, you can find it from this link. And what you will find, okay, so we can click it. So if you go to this page, and then you can find a link to JAX codes and then TensorFlow codes, and also, well, the actual codes are here, but then you can run them in Colab. So this is, for example, the TensorFlow implementation of parallelization of the Kalman filter and smoother. So what it looks like is that, well, these are the imports. So the associated scan is actually in the TensorFlow probability library. And then, okay, so we make our life easier by defining these shorthands or storing the function in these variables. And so this is the model which is constructed. So this is a classic Wiener velocity model, which is used a lot in target tracking. But anyway, this is like a canonical example of a state space, linear Gaussian state space model. So all you need to do is that it has that kind of form, or you need to know that it's this kind of form where this f is something and h is something, and then we have the covariance, and the covariance is for the process noise and the measurement noise. And this just makes the tracking model. And then, okay, we call it. Then we have a simulation of data. So the data looks something like this. So there's a car going on, and we get measurements from it. And then, okay, this is calling the data generation. Then the sequence of Kalman filters is smoother. So if you have been using TensorFlow, then over there, well, when you write loops, you don't want to use for loops at all, but instead you use more like a functional loop. So there is also that scan operation, not the associative scan, but just a normal scan operation, which is related to for loop. So what it does is that it calls this body by, so that it gives these observations as or this argument like one by one here, and then there's a carry argument, which is so you initialize by something, and then you always return like a updated version. So it's a functional version of a for loop. So this would be just an implementation of a classical sequential Kalman filter by using that primitive. So there's a prediction step here, and then the update step is implemented by this. But this is sequential. So for sure we can run it like this on a GPU in TensorFlow, but it's going to be not parallelizable because it's like a sequential loop. And the smoother using the same primitive would look like this. So we can do a backward loop. And this just implements the something called Rautungsriebel smoother. Okay, so this will be the result. So there's a tracking result for the filter and smoother. So how to do the parallel one? Okay, so the first here is just a Python demonstration how we can do, well, as I mentioned, is that the prefix sums is basically cumulative sum. So this would be the sequential way to compute just all prefix sums for an array or cumulative sum. So it's a sequence and it takes a linear time, even in parallel computer. But then if we want to compute the prefix sum using the playlogs method, so I showed you the MATLAB version of the playlogs methods already, and it's also possible to do the corresponding Python version, which looks like this. So this is not yet parallel because this is just simulating things. So this is the array, and then we have the up pass. So we only need to kind of loop over the levels of the tree. And then this could be parallel, but there's no easy way to make this parallel within vanilla Python. But anyway, this is the part which could be parallel. And in the down pass, we also loop over the tree levels, and this would be parallelized. And then, well, we get the same result for the array. Now the filter, especially the Kalman filter, which we are discussing, is that, well, we had this, this was the operator, which was defined like this. And then we had the Kalman filter version, which looked like this. So these are the elements, or this is the element, and these are the operator operations. So when we implement this, that, okay, so we need to initialize first. Okay, so there are some details which are only in the article, but what this does is that this just returns those initialized elements on an array of these. Actually, there are sometimes TensorFlow code is hard to read. So this initializes one part, and this initializes in parallel the rest of them. So in the end, we get tensors of the elements out from this. Well, actually, so this is the actual initialization routine. So this does the initializations in parallel and returns those tensors of the elements. Then, so this is implementing that filtering operator then. So this is exactly this. So in TensorFlow, when we implement it, well, so this is actually working so that we're using the batch dimensions for parallelization. So if you're familiar with the TensorFlow, this batch dimension, which is the one which is typically used for parallelizing things. So that this just takes the elements out from the arguments, and then these exactly implement those operators that we have, and then we return the combined elements, or actually batch of the combined elements. And then if we actually implement the parallel routine, we only need to do the initialization here, and then we call the associative scan with this filtering operator. And then this happens to return exactly the filtering result, because that's what our theory says. And then we can compute that in, well, compute the filtering result by doing that. And if we do that in GPU, then this routine gets automatically parallelized, because it's a parallel routine which does that prefix sums computation using the playlogs methods. And then, okay, so we can check that the result is the same. And then the same also can be used for the smoother. So we can initialize the smoothing elements. Or initialize, and the smoothing operator then looks like this, which was also in the slides. So this one here. And then, so this is the actually implementation. So we just initialize, well, actually we initialize more like, okay, here, well, these are the elements, and then we call the associative scan. And that's it. And then because we are in Colab, we can even run that in GPU. Maybe I'm not going to run it, but this is a runtime comparison, which actually produces those plots, which I have over there. But if you're interested, so there's also a JAX version available here. But you can maybe take a look at that yourself. Okay. I think that we have some time for questions as well, Alex. So if you, I guess it would be good time for that.
Yeah, thanks a lot, Simo, for this excellent talk. Really amazing to see, in particular, how deep mathematical and abstract mathematical concepts like associativity can be exploited or ends up in having better implementations of software, like faster algorithms. That's really cool. That was really an advertisement for mathematics.
Yes, yes. Excellent. Mathematics is important in the world. Yes. I agree.
Can help you. I was just thinking, because I remember a long time ago, I did an internship in Siemens in a signal processing department and spent a summer in implementing a fast Fourier transform. So is a discrete Fourier transform also a potential target of this all prefix sum methodology? By accident, did you think about computing discrete Fourier transforms in parallel?
Well, I guess in discrete Fourier transform, there's a chance. So like that vanilla implementation is quadratic. Mm-hmm. And then you can use the classic like butterflying thing to make it n log n. Yeah. But I know that there are ways to parallelize those fast Fourier transforms as well. But mm-hmm. I'm afraid that this prefix sums method might not be the right one, because the prefix sums methods are good for case that you have a linear method, which is somehow like there's a clear sequence. Yeah. Then that can be applied. But I'm not sure. So there's a way to parallelize them. It's possible also that it's actually related. Yeah. But
I was just wondering if you came across or played with it in an example in one of your papers. But thanks a lot again.
Thank you.
Yeah. Are there any other questions? I hope we can get your slides and I can put them on the school site.
Yes,
Simo.
I can send this.
Also, yes, I will now do some post editing of the lecture recording and ask for your approval. Yeah, here's one question: is there any implementation for Viterbi?
We have been working on some implementations, but they are not yet in the shape that we could publish them. So there will be. If you want to ask for them, you could contact Sakira, who is the first author here. So Sakira Hassan could actually send them to you if you want them.
Excellent. Yeah, then let's wrap it up. Thanks a lot again, Simo.
Okay,
really
thank you.
Brilliant lecture. And yeah, have a nice rest of day. Bye.
Yes, you do. Thank you.